Hello, 5th period class. I wasn't able to get the class started today with you guys, so I made the video notes that'll get us caught up to where we need to be. This is where we left off yesterday. We were talking about these two distributions and the location of the mean, median, and mode for each one. So skewed distributions, the mean is kind of pulled to the direction of the skewness. A couple of things to look at. We talked about these briefly, but first of all, on this side, the median is the middle data value. So it's had, you can consider that like an equal area. So the median, the center value, so there's like 1 unit here, 1 unit there, matching units on the left side, and then the median is right in the center in the event that there's one in the very center. Here's another picture of the median. You can see there's 3 units on the right and 3 units on the left, and that's the center there. You would take the average of these two values for the median. So think of that as equal area. The mean, on the other hand, is like a balancing point of the distribution. So if you want to have a similar idea of area, what you really need to think about here is volume. So not only does it matter how many data values you have to the right and to the left, it also makes a difference about what their magnitude is. So how far away they are, or what their data value is itself. So you would see how many data values you have, and then the count of data values, and then times their actual numeric value. So that gives them a weight. So it's distance away, or their data value, times the frequency. So it almost becomes like a volume measure. Okay, so this would give us the mean of this data set. These values are closer to that mean, but there's more of them. These values are further away, giving these kind of more weight to the mean. Here's a few other examples that show the mean, median, and mode locations for different types of data sets. So here's that theoretical bell curve, unimodal and symmetric. This one happens to be perfectly symmetric. And you can see the mean, median, and mode all line up at the exact same place. So mean is the x-bar, median m sub d, mode m sub o. They all line up. There's no skewness at all. Everything lines up. Here's a kind of a unique distribution. This is a bimodal distribution that is also perfectly symmetric. So the perfectly symmetric distribution is going to have the mean right in the middle. The median is right in the middle. Those would be lined up together with perfect symmetry. In this case, there's 2 modes, and those are just the highest points on the graph. For a left skewed distribution, the mode, easiest thing to find, I think. It's the highest value. The median will be to the left of that. Remember, the median shows equal area, so that means that the number of data values represented on the left of the median is the same as the number of data values represented on the right. I think I said that backwards. On the left and on the right is the same number of data values. The mean, though, is even further left than that. The mean is being pulled down toward the negative values by that skewness. Similarly, the right skewed distribution, the mode is still the tallest point. The median is going to be just to the right of it with equal area on either side of it, and then the mean is being pulled this way, so it's furthest to the right. It's being pulled by these high numbers on the right-hand side. And then here's that seesaw type problem. I like to call it the seesaw problem. You can have a lot of data values on one side of the mean. This is the mean. You can have a lot of data values on one side of the mean. The magnitude of those values are individually not as large as this one value way out here, which is having a big effect on what the mean is going to be. The mean is being pulled this way by this value. Now, it's not very close to 25, but it's also not in the midst of these 7 data values. If the 25 wasn't there, the mean would be somewhere closer to the middle of these data values. But because of this, the mean is being, again, pulled to the right. This is a right skewed distribution. Okay, on to the next page. When we're trying to find a mean from a frequency table, it's a little bit different because we don't have all the data values. So we've seen this example before. Here's our frequency distribution of these heights of black cherry trees. Here's the thing. If we wanted the mean of this data set, we don't actually know the individual data values. Remember, say for example, this first bar, the values in here could be anywhere from 60 to say 64 feet in height. There's 3 data values in here, but I don't know exactly what those 3 are. So what we do on the table is this. We have the frequency, it tells us how many are in each bar. And we have the class, which tells us the range of values or the interval included in each bar. What we want to calculate is this new thing called class mark. And we're going to use this as basically as our variable. The class mark is found by just averaging the boundaries of the class. So 60 to 64, that's not what I meant to do. I meant 64 minus 60 divided by 2 will give us the average value, and that actually comes out to 62. The average value here would be 67. The average value here would be 72, and so forth. 77, 82, 87. Again, keep in mind, I don't know what these values are exactly. What I'm going to do is I'm going to assume that they're all 62. On average, it works out. I'm going to assume I have 3 data values that are 62 each. So I got 62, 62, 62, 67, 67, 67, a bunch of 72s, and so forth. Next thing I'm going to do, because I do want the average, I'm going to pretend like these are all the values and they occur with this frequency. In order to figure out kind of the weighting of each of these, I have to multiply the x value, the class mark, times its frequency. So 62 times 3, 186. I'll write here what I'm doing. 62 times 3, 186. And if we continue that for the rest of them, we get 67 times 3, that's 201. And I'm just going to go ahead and give you the rest of the values. Hopefully you can understand where these are coming from. 576, 770, 410, and 174. So this basically represents the sum of 3 62s, 3 67s, 8 72s, 10 77s. And we're going to actually pretend like this is our real data. And if you remember for averages, what do? You add up all the data values and divide by how many you have. So we're going to add all these up. And I like to just show the sum there. I've already added these up for us. It's 2,317. If you recall how many data values we had from when we did this previously, there's 31. So this is information you're going to need. And basically, we're going to estimate the mean with the frequency table by doing this. The mean is going to be, we can still show it with x bar, but it's kind of, it's an estimate, okay? And we'll call it a weighted mean. We'll talk about that in a second. It's the sum of this. I realize you can't see what I'm writing. It's the sum of the last column. So it's the sum of all the x times f values divided by n, which is the sample size. Okay, so 2,317 is the sum of the last column divided by 31. Equals 74.7419 and a bunch of change. This is actually called the weighted mean. Weighted mean. The reason why, we don't know this individual tree heights. So we're going to just use the center of the class to get an average. And then by doing this multiplication going across, we're basically more heavily weighting, say, the 77. We're pretty heavily weighting the 72. The 62 doesn't get weighted as much. The weighting depends on the frequency of each line item. So we refer to this as finding the weighted mean because we use a single tree height times the frequency to weight the occurrence or to weight the frequency of that particular bar. Okay, so we weight, let's do this, the average, the mean, is weighted by class marks with greater frequencies. They have more of an influence on the total because they generated more of the numerator values, which are right here. Hopefully that makes sense to you. So I'm going to stop this set of notes right here because this takes care of your period 5 catch-up needs for today. I'm going to generate a second video that talks about standard deviation.